about the homework. We briefly, we talked yesterday during the homework session, answer questions. So yesterday we assigned a homework called counter.v. Today's homework is called stack.v, which is a layer built above counter.v. So we want to make sure there's enough time. People can ask questions now instead of using time during the homework sessions. So I will let Jeremy talk about this first, and then in the second half of this lecture, we will go back to talk about how to apply these layers to build the actual CertikOS OS kernel. Okay, Jeremy.
Right. So I guess I'll start by summarizing again what we did yesterday and answer any questions you have about that. So yesterday we started from this base layer with nothing in it. That's called base L. And then on top of that, we implemented a simple bounded counter. So the idea here is we have a function getCounter, a function to increment, and a function to decrement. Then we gave some low-level specifications that capture the behavior of this code, but still in terms of this trivial base layer. So these low-level specifications are gathered in a layer interface called counter sigma. And we showed that the code implements those low-level specifications faithfully with the simulation relation, the identity relation. The next thing we did is we introduced a new layer interface, a higher level one, called counter L that had these primitives that abstract what the code does. And whereas at the base layer, the abstract state was of type unit, because there's nothing there. Here, we kind of hid the counter variable that we used to implement this counter. And instead, we introduced this counter abstract state component of type nat, right? So now we're doing things in terms, as we build up, we're going to do things in terms of this high-level cog type rather than the low-level binary representation of integers in CompCert and the details associating with reading that from the memory and so on. So what I'm going to present today is, on top of that counter L layer, build another layer called stack. And the idea is that stack will use the counter from the layer below to index into an array of integers and store the elements on the stack in that array. And then we will abstract this array by a list of cognat integers. So I want to point out also before I start, the cogdoc for the code of the tutorial is available at this address that you can't read. So that's this URL, certikos.github.io.
Should be already posted.
It's posted, but if you want to look it up now, the link is this one, tutorial-cogdoc. /toc.html will give you this nice index with all the files involved in this tutorial, including the code of compcert and of our liblayers library that we're using to build these layers. So if you want to browse the code and be able to follow the definitions into the documentation, you'll be able to do that. So I guess first I should take any questions about yesterday's homework or about what I talked about yesterday. Yes?
So one of the challenges when I was doing one of the counterexamples last night was that I didn't have that much information on the lemmas and functions for working with memory.
Right.
So is that in this CogDoc, or could we have a bit more, given that at least that proof involved working with it, could we have a bit more information on, in an informal sense, the interface that we'll be using to memory?
Right. So two things. Yes, you can find some of it in this CogDoc, and I may do that just now. And also what I'm going to do today, yesterday I gave you, I went over the whole file counter.v so that you have a sense of how everything fits together. Today what I'm going to do is I'm going to step in detail over the code proof and the refinement proof for the push function in the stack, and so some of that will come up. If you want to go and look up, for instance, the interface for this memload function, see what's happening here, you can follow the link. And this file defines all of the operations in the compcert memory model. Right. Part of the difficulty with this tutorial is there's a lot of compcert and so on that we're using. So if you have never been exposed to that, that's tricky to get acquainted with. But using this CogDoc file, you can try to read about the memory model, for instance. Other questions? Does that answer your?
Which file was this exactly? This is not
No, this is compcert.common.memtype.
Okay, I was looking in memory data.
Right, okay. So memory data explains how we construct a new, oh no, memory data is the base types used for the building this. Any other questions about the homework or things I discussed yesterday? So to give you a similar summary of, if there's no questions, to give you a similar summary of what we're going to do today, we'll start from this counter layer. That provides get counter, increment counter, and decrement. And on top of that, we build a stack layer with a function getSize, function push, a function pop. We show they implement some low-level specifications in counter sigma, in stack sigma, and then show that these low-level specifications can be abstracted or refined into this stack layer. Right? That has this get size, push, and pop primitives, but that are expressed in terms of this abstract data component called stack that will be of type list_nat, and where we will maintain the invariant that the length of this list is less than the maximum value for the counter. And so what I'm going to do is show you some of the basic definitions for this new layer, and then we're going to focus on push. And I'm going to step through the code proof and the refinement proof for push so that we can discuss the details of that. So first, let's have a look at the code. Those are the functions implemented in counter.v. And now we introduce on top of that counter layer an array stack that will contain the elements of our stack. The getSize function simply returns the current value of the counter. But one reason we introduce a new function here is that in terms of the specification, here it will be the length of this stack list, whereas here it will be the value of the counter, right? So the push function that we're going to focus on first reads the current value of the counter, increments the counter, then stores the value that we want to push on the stack at this index that we came up with. And finally, pop does the opposite, decrements the counter, and returns the value. So here we're assuming the user is not going to go beyond the bound. And so our specification will say, if you push while the stack is already full, that's a crash of your program. And I make no guarantees.
In practice, though, what will happen is you just replace the top of the stack with the new value, right? Because the counter is bounded.
Because the inc counter does that. That's possible, yes. But yesterday we saw that if you increment your counter beyond the limit, then this high-level specification makes no guarantee. So we can't prove that that's what will happen in practice. Any other questions about what's happening here? All right. So first, I'm going to go quickly over this definition of the kinds of abstract states that we're going to use for this stack. So we have a stack that's a list of integers. That's a Z. That's the one component of our abstract state, and the initial value for that will be the empty list. And the invariant that we're going to maintain is that the length of this list is at most max counter. We prove some properties about that, package them into this layer data record that has all we need for the abstract data at this layer. If that's clear, I'm going to now show you the high-level specification for push. So here, this specification will tell us what happens when I call push in terms of this abstract data that I just defined. So what's happening here is first the specification will check whether indeed there's enough room left in our stack, right? If that's the case, then the new value of the stack will simply read out the argument as a signed integer, right? So this is a int argument, and so it's simply a 32 bits or 64 bits representation of an integer. We need to specify that we want to interpret it as a signed integer so that we map it into an ideal integer z as implemented by Koch. So here we use z sign instead of z to specify that's what we want. And so the new top of the stack will be the value of this argument translated to an integer, and the rest of the stack will be the previous contents. If there is no room left, then my specification simply says, oh, I get stuck, I don't do anything, I crash, no guarantee. Is that any questions about this high-level specification? So now to implement this push function, we're going to first need to import the code of the push function. And as before, we have this function that we pipe through the CLightGen utility that gives us this code, but as a CompCert CLightAST. So that's what happens here. The CompCert function fpush will return void, use the regular calling convention. It will have one parameter that I will call pushX, and that will be of type int. It will have no local variables. It will have one temporary variable, so that's the one that we have here, the index that we're going to read out of the counter. And the code will be this. So it will be a sequence of first the call to this getCounter function of the underlay, right? So here we're calling a primitive from the layer below. Then we're going to call incCounter, another primitive from the layer below. And this is the ugly CLightAST version of writing into the array. We need to package this into this auxiliary function definition with some inlining information for the benefit of our compiler. But I'm not going to go over the details of this. Rather, I'm going to show you next the low-level specification that captures the behavior of that, which is push step is defined here. Can you still read this?
Yes.
OK. So as before, we define this step relation between the initial call state of the function with a certain value for the arguments to the return value and final state, final memory, final abstract data. So we need to look up the memory block SB where the stack is stored. We need to know what the result is going to be to call the counter primitive from the layer below. And to do that, we can simply reuse the get counter high spec, right? And it says, if I call get counter, then the result will be an integer representation of this index. Then we need to do the same thing. Know what's going to happen. We assert that when we call the increment primitive in the layer below, it's going to give us a new index prime, right? What we will then do is store into the memory at this address that we obtain by multiplying the index by 4, which is the size of each entry. And if all these constraints hold, then our low-level specification will take a step from being called with this argument x in the memory state M with abstract data D, and returning no value in the memory state M prime with the new abstract data G prime. So with all of this defined, if you don't have any questions, we're ready to go into the actual code proof and step through this. If I run it in an environment with the right version, of Coq installed. So what we're proving here is that on top of the underlay counter, this mpush tiny module that contains only the push function will implement the one primitive tiny layer interface that contains our high-level specification for push. All right, so the first step in this proof is going to invoke this code proof tag. So the idea behind the code proof tag is that our goal here is in this weird format, and what we want to do is have this tactic take care of all the administrative stuff and unfold everything so that we can get to a place where we have this simulation diagram to prove. And the simulation diagram says, if I have this hypothesis C step that says my low-level primitive takes a step from MD to M prime D prime, right? And so that's the spec. Then I want to show that the execution of this push function will do the same thing. And since the simulation relation is the identity, we don't really, that's why this diagram only has one initial state and one final state, right? Hello? That's going to be a problem.
Is your laptop on, or is it just the projector that's?
No, it's my laptop that's. No, for some reason my charger is not working. It's working now, but
Is the sound? Okay.
yeah. Sorry about that. I'll need a couple of minutes to. Yeah, I think that's good. But, So what's going to happen here to kind of preview this for you is, so my specification tells me, oh, this is the final state. And so here we'll have to unroll the C-Lite operational semantics from compcert and execute these three statements that are in my push function to show that in the end we'll get to that same final state. So that in practice, this is any number of steps of the C-Lite semantics will get us there. And so we'll have one step that will be calling get counter, one step that will be inc, and one step that will be this array access, where we'll write our new value. Do you have any questions about anything so far? Question?
So I can imagine for slightly larger code examples that actually writing these ASTs would be a huge pain. Do you guys have, like, on the software engineering side, some way of typing or like generating the ASTs that you're?
So these ASTs we come up with by using this C-Lite gen utilities that's provided with compcert. So we do that, copy and paste, and this kind of thing. Generally speaking, our code proofs at each layer are kind of a little bit intricate because we use the compcert semantics directly. We don't have an official program logic or anything. So that's kind of our current state, which is we have a very good way to deal with the high-level structure of the system and do this refinement. And for an operating system, that's the most important thing. And the algorithms themselves are not that involved so that we can get away with using this very primitive way to deal with code proofs. But part of our research agenda is, can we come up with a slightly higher level language that still allows us to encode all the nasty details of bit representations and so on, but that can directly give us the C code and the low-level specification and a proof that these two are related. So that's one of the directions that we want to go to improve this. Any other questions? So this code proof tag tells us, oh, so we have this step of the specification, and we want this step of the code. So unfolding some of that, it will give us this push step. That's the low-level specification that we just saw. And this step that represents the execution of the code. So first thing we are going to have to do is, because we're invoking the primitive get counter, we'll need to know what memory block ID CompSert has assigned to this primitive. So our tactic find prim allows us to do that. And so looking at the result, it will tell us, oh, there's this memory block. If I look up get counter in the environment, it will give me that memory block. And the information for this function in the global environment will be what you expect from get counter. We do the same thing for inc counter that we're going to need to use too. And now we're ready to kind of destruct our specification steps so that all of these constraints that we specified, we get them as hypotheses in our context. So looking at it again, we know that the stack is stored at the memory block SB, that the current value of the counter is this index, that incrementing it will give us this new abstract data and return that d prime and return that value. And that to get m prime, what we had to do was to store this value x bundled into a CompSert value using vint and store that at the address specified here 4 times our new index. So now the next step is we have to so first of all, we can examine exactly what it means to increment this counter and see that we have this test first. So if you look at this hypothesis, we know that the result is some value, right? We know that it worked when we called get counter, no, inc counter. And so what we want to do here is destruct this test. And in one branch, we'll have a hypothesis of type counter d less than max counter. And we'll know that this term here will be equal to that term. And then in the other branch, we'll have the opposite hypothesis here, and we'll know that none equals some. So by inverting this, the result of that, we'll be able to eliminate quickly the branch that asserts that none equals some by contradiction, and be left with this shorter version of H8, if I can find it. Oh, no. It will have replaced this d prime by the new value of the data here. You can see that in the Go. Next, we prove that the value of this index is actually the value of the counter we had in our initial abstract data. So this is not the interesting part, so I'm going to skip over it. But we have this lemma that tells us, oh, the index is within these bounds. And by looking in more detail in H5 at what it means to get the counter, we'll be able to relate these two quantities. And next, we're ready to start executing the code, so to speak. Any questions so far about what's happening? It's a little bit hard to follow because there are all these details involved with the CompSert model of the semantics and so on, and the representation of integers. So again, this tactic C' step will be another layer of removing the administrative stuff and getting to the actual CompSert semantics now. So we know we have to do 0 or more steps of this function push that we have. With this environment that contain the value of the local variable x. Expanding this a little bit gives us the actual code that we'll have to execute. So here you may recognize the code of push, which is a sequence of a call to get counter, then a call to inc counter, and then this assignment statement that's going to actually write into the array. This step tag will actually try and take a step of the C-Lite semantics. And so we're going to repeat it as much as we can. And what we're going to be left with are these 3 sub-goals that correspond to the side conditions in the CompSert semantics for the execution of these 3 statements. That we'll have to prove to make sure C-Lite takes the correct step. So the first one is that the return value of getCounter should be as expected. And thankfully, we can use hypothesis H5 here to show that very quickly. So H5 tells us getCounter high spec. Oops. GetCounter high spec will have this result. And by reflexivity, we can unify the 2 existential variables that were introduced when we applied the steps of C-Lite and show that this thing work out. Then we do the same thing for the increment step. It's only slightly more involved. We know that this test succeeds the decide counter less than max counter because we had the same test in our own low-level specification. Likewise, so here H2 tells us this new index is the old value of the counter plus 1. And as before, that's enough to show that the resulting state is good. And finally, the most complicated side condition is we have to show that storing into this stack array using this piece of C-Lite program gave us the new memory state that we want, right? So we have a lemma that tells us, oh, this index is less than max unsigned. That's so that we can go between the 32-bit representation and the integer representation. We have this other lemma that tells us we can do that not only for 32-bit integers, but even for pointer integers. And so unfolding everything that we need, that leaves us with this goal. So this goal was generated by the C-Lite semantics. And it will tell us if I store this value at this address in the block SB that contains the stack and the memory state M, and then generate the new final states from the result of that, that should be identical to the final state of our whole computation. And we can, in fact, show that, first of all, by showing that store succeeds from the hypothesis we had in our low-level specification. So to do that, we need to tame a little bit this offset by using the properties of machine integers that are provided by CompCert, right? So this PTR offset module has a number of lemmas about these PTR offset integers that you'll be able to use to deal with this kind of situations. So here we handle some of that, so that now we've boiled down this complicated 32-bit pointer expression to this much nicer integer index. And again, using our hypothesis from the low-level specification, we're able to finish this proof. So that's our first step. We were able to prove that our code actually implements our low-level specification. That's a little bit hairy. You have to go through it yourself and look up these lemmas and so on that we use for it to make more sense. But if you have any questions, I can answer them now. Yes?
So as a general comment, there's just like a lot of noise in the hypotheses. Is there any way we can hide some of that or clear those out, or those used implicitly by the tactics? Is there just some way we can reduce the total volume of what we're looking at? It seems like a lot of it's not super important to the proof itself.
I believe most of them are necessary at some point.
Okay. I guess what I'm saying is we don't explicitly use a good amount of them, right? But they're used by the tactics, is what you're saying?
So we can look at them, actually. Yeah, so some of these are used by the tactic that applies the C-light semantics, right? So, for instance, these hypotheses that give us the memory address of these functions that we use are necessary because of the C-light semantics. And the rest of them are pretty much the hypotheses that we had in our low-level specification and that are necessary to finish the proof. So unfortunately, there's not much we can do about that. Any other questions? So maybe I can try and show you how the refinement proof is going to go now. To do that, I need to tell you about these two relations that will specify how our high-level data is encoded in the memory, both using the abstract data of this counter layer, but also using this stack array that we introduce. And so the general pattern for that again, is that we'll have the concrete memory and abstract data at the stack layer that will correspond to the concrete memory and abstract data at the counter layer by this match relation. So match will tell us how is this data encoded in the concrete memory, and a relate relation here that will tell us the relationship between the abstract data at both layers. So looking at our actual definition here, match will tell us, so for the match relation, since this is a list, we have to define an inductive predicate that goes over the whole list and look at how it is encoded in memory. So we use this match stack predicate that, given a memory state, a block where the stack is stored, and an index into that block, we will know that this list is encoded at this address, right? So we know that at the address 0, no matter what, we encode the stack nil. And we know that if we can encode the stack up to index, and that this stack is, the tail of the stack is stored up to that point, and if it's the case that reading the array at this address gives us the result x, then we'll know that this whole thing encodes the stack with one more element on top, right? And here you'll notice the list has the top of the stack on the left, but the array has the top of the stack on the right. So that's how the stack is encoded in memory. And the relationship between the two abstract data components so yeah, we use this inductive predicate to define this predicate about the whole thing, right? So if the whole stack is encoded, then we're good. And the relate component will simply assert that the length of our stack as a list is the same as the value of the counter from the underlay. We package these two components into this abstraction relation, prove that it has some of the properties that we need. For instance, that the initial states are related the way we want. And finally, manage to define this relation stack R that we'll be able to use to do our refinement proof. Any questions about that?
So can you just summarize in words what stack R means?
So stack R is the way we're going to show the relation that we're going to use for this simulation diagram. So that's what it means. And it's constructed from these two match and relate components that I showed to you.
It's more complex than the relation showed, in the first lecture, like the one, because now we have C memory, as a component and abstract state. So that's why we need these two components.
And for the code proof, we use the identity relation, right?
And the intention, even though Jeremy showed the code proof, the intention is the majority of the code proof can be automated. So in the future, we will likely synthesize the C directly from the low-level spec, because that indeed is most of the cases very straightforward, because it's almost just reinterpret the the C code directly. There's nothing magic going on in that step.
So now using this stack R relation that we just defined, we can state what we want for this refinement proof, right? Which is that on top of this single primitive layer interface here that contains our low-level specification, by adding no code, we'll be able to implement this single primitive layer specification, layer interface that contains the high-level specification for push. And so, similar to before, we can start with this refined proof tag that unfolds this goal to give us the simulation diagram that we want to prove. And so, telling you a little bit about this. Now the simulation diagram is slightly more complicated, right? Because we have this non-trivial relation between the initial states and the final states. So we know that if we take a step from xm, xd here, and there's a step of our high-level specification that takes us to xm prime and xd prime. And if we know that this xm, xd state is related to this ym, yd state by our stack R, then they should exist a step of the low-level specification that takes us to a state here that is related to the final state of the high-level specification, again by stack R. So as before, we're going to first work on this hypothesis that we have to kind of extract all the facts that we can from the fact that the high-level specification makes this step. So this is not... Looking at what this inv gave us, we now know that it's by interpreting this push high spec, we took a step from xd to xd prime. And we know that this high-level primitive doesn't touch the concrete memory. Working one step further using this inv generic sem tactic that we can use to inverse steps of this kind. We can get there. So simplifying this. Distracting this again. Right, we have the hypothesis that we want. We know that this push high spec gives us the new abstract data xd prime. Inverse hypes here will allow us to kind of peel off this relation here between the list of arguments that we have here and these y args, right? So we know here that we called this function with one argument I, and we know that this list of arguments is related to the one at the low level. So the role of this next tactic is to decompose Y args so that in our goal here, we will have the actual value to work with. Right. So now we have this value of the argument in the goal that uses our low-level specification. Working on the memory component now, we know that we have this match relation that we defined that relates our two memory states. So I've destructed that hypothesis that related these two memory states. And now I have these relate and match components that are accessible. So if I open up those two, now I can access those in terms of this match stack predicate that I defined between my stack and the concrete memory, my stack as a list and the concrete memory. And I know about the length of this thing. And so what did I do that broke this proof?
After in H0, there is a in monad H1 using the base.
Oh. Here.
Can you describe what inverse hypes does in general?
So yeah, in general, it looks in the context for pairs of CompSert values that are related. And so you'll have things like match val. And you'll know on the left, for instance, you have a specific kind of value, let's say v float 314. And here you'll have a variable x that shows up all the time because our simulation relations are constructed in terms of this elementary match val. So it scans the context for hypothesis of this form, and from this you can deduce that x is itself a floating point value with that same value. And here it was able also to work on a list of value, in which case it will destruct this list element by element and do the same thing. Does it make sense? Right, so here, this inv-monad tactic simply puts H2 in a more usable form. Then when we unfolded the high-level specification, we have this test, and the tactic dest in will simply look for a thing to destruct in that hypothesis. In this case, it's this decide test that we're working on. And so we destruct this decide and do the inversion as showed up in the code proof. And we can discard the negative case where our high-level specification will have returned none. So the next thing we need to make sure is that we can indeed store a value at that address in memory, right? Because we want to know that the CompCert store will succeed, so that we can show that our low-level specification will indeed take a step. So here we use this lemma to do that. That says, oh, if I can write at this address in the memory, then indeed there exists a new memory state, and the store will result in this new memory state, will succeed and take me to this new memory state. And to do that, we're going to use some hypotheses that come from the fact that these two states are related, which say that in stack R we also have declared this new variable stack. And so this relation also says, yes, here we have a stack global variable and permissions to access it, whereas here we have nothing because it's been replaced by the abstract state. So I won't go over this part in detail because it's already quite late, but from this we can deduce that store succeeds, and that's the first step to compute our new state. Yes?
So when I was looking through the proof for buying, this destructive valid access store was the point where I went, where in the world did that come from? Because it's not in any of the goals, it's not in any of the premises, and so is it just implicit in that your store, that you, in that the store, the goals and premises involve a store, and so you have to know that that's valid?
Is your question, how the hell am I supposed to come up with this? Or so, yes, the only way you can come up with this is examine the other examples and see that's how we prove that our store succeeds, right? So, yes. In terms of where does this lemma come from, it's one of the properties of the CompCert memory model that relates the permissions we have on different parts of the memory and the fact that store succeeds. Wolf?
Just to sort of add to that, where you come up with it, if you don't have that and you just proceed with the proof, you'll find at some point you need to know that that store thing exists. So then you'll have to look for how can I prove that the store exists, and then you go back and add it. So if it wasn't there, you would eventually find the proof that you needed, and then you can add it. So that's how you come up with it if you don't have an example to look at.
So now that we've gathered all these facts and so on, we're ready to actually show that our low-level specification will do what we expect. So introducing existential variable for these three components, the return value, the new memory state, and the new abstract data, we'll then have two sub-goals. One, to show that indeed my low-level specification takes this step, and the other one to show that indeed the new memory state that I've introduced is related to the final memory state at the high level. And so I don't know into how much detail I want to go here, but again, we need to show that our index is in the range where it can be converted to a 32-bit integer. We're going to say, oh, we can actually apply the constructor for the low-level specification to show that we have this transition. And so the things that we have to prove next are all these hypotheses we had when we defined the low-level specification. First, that getting the current value of the counter gives us this index, that incrementing it gives us this new index, and that storing a value at this address in the memory will give us a new memory state. And so that's what happens here. We use some of these theorems about going from one representation to the next to prove that the indices end up being what we need. And from the store hypothesis that we got before, we can simply rewrite this index here that first goes from 32-bit integers to Coq integers and back. And then use our store hypothesis here and this range hypothesis that we just introduced to discharge the side conditions. Next, we need to show that this new state that we just introduced and proved that the low-level specification takes us to that state, we need to show that it's actually related to the high-level specification. So in terms of this match val thing, that's for the return value. So in both cases, the return value is, oops, v and def, because push does not return anything. So that's easy to show. And next, we need to show the match component and the relate component. So this match mem encapsulates these two things by as well as a memory extension here between these two memories. Thankfully, the memory extensions are preserved by store. And so this lemma of the COMSERT memory model tells us, oh, if you have an extension between M1 and M2, and you store something in M2 prime, M2 to get M2 prime, that you don't have permission in the other memory at that address, then this M2 prime is still has everything that in the M1, in the memory here, right? So in the memory here, there's nothing here. So if I only modify the memory there in that same region, I won't break this extension condition. And now we're down to the interesting part where there's this relate component and this match component. The relate component just told us the size of the list is the same as the value of the counter. Thankfully here, our list has one more and our counter has one more, so that, oops. It's quite easy to show that these two values are equal. We can simply use the omega tactic. For the match component, things are a little bit more involved, but again, we simply added a new element in the beginning of the list. So we can reuse the match that we knew on the initial state for the tail of the stack and simply have to prove that at this new index, the two are related. So we can do that using match store. And using this constructor, match stack store, which told us, oh, if I have two stacks that match and I store a new value, and I add a new element, a corresponding element in the front of the stack, then I can derive the match stack for one more value. And finally, this is a side condition that we have where we need to show that we need to show this condition that in the new memory, this invariant is preserved. We still have no permissions here, and we still have permissions here.
So when you said the invariant is preserved, you meant the permissions invariant and the permission variant are preserved?
Yes, yes. Because we modified the concrete memory here. So we need to show that this property still holds, that newly introduced global variables, we can access them at the low level layer, but we can't access them at the high level layer. And so this, this match perms match memperms hypothesis, we already used it before, and we derived it from the fact that these two states are related. Now we need to establish it again. So we specialize it to get what we need for this goal. Destruct these two components, one that asserts there's no permission, the other one that asserts that there are permissions. And using those, so the fact that there's no permission is straightforward because here we didn't modify the memory, right? But the fact that there are permissions here is simply comes from the fact that in the CompStat memory model, when you do a store, the permissions are not modified. So that's what this lemma that I'm going to apply here asserts, basically. Finally, we need to show that the next block component of the memory didn't go backward, basically. And that's the same kind of thing where here we didn't modify the memory at all, And here we executed a store operation that did not modify next block. So next block is the value in the CompSert memory model where all blocks up to that value have been allocated. And if you allocate a new block, it's gonna give you the next one. But, right, so using the fact that store did not change next block, I can simply prove that by using the corresponding hypothesis on the initial states. And that's it. We now have both our code proof and our refinement proof, and we were able to prove that this push function, when I run it on top of this counter layer, indeed implements its high-level specification in terms of this abstract data of the stack represented as a list. Question?
So this is not a question related to content, but so maybe other people in the room could answer or help answering this question. But like related to other lecture, how much do you think that this old code would be possible to shrink using like LDAX and like make more use of automation? So these tools, they seem to be quite involved, and maybe there is space for automation. So I'm not a code user, an experienced code user, so I'm really asking.
Right, so there's gigantic space for automation. And indeed, the focus of our research effort until now has been mostly on these high-level abstraction structures and so on. So Professor Shao mentioned before our effort to come up with a language to generate low-level specifications and C code from a common component. So that's one thing we can do. You can imagine connecting the VST logic to be able to do these C-Lite code proofs. So there are different directions we could go in, and definitely the goal is one day to have most of this automated away. Right?
So I can add that we actually already defined quite a lot of tactics in our existing libraries. And based on my own experience, I feel like that sometimes predictability is more important than introducing some LTAC routines that actually sometimes fails. So we didn't feel like what we have used so far is a major impediment of the verification effort. And often, you know, the hardest part of all these proofs is always order of magnitude harder than the rest of the proof. And most of these proofs we have done so far is, you know, reasonably straightforward. But, you know, that's on top of what Jeremy has already answered. That is, there's definitely room for improvement, but we don't feel like that's the critical aspect of this current project.
Yeah, I think the learning curve is very high because there's all these all these details involved with CompSert and so on that are involved. And so if you have never seen anything like that before, it's very scary. But on the other hand, the fact that even with such a rudimentary framework, we were able to verify CertikOS, I think it tells you a lot about how much this high-level decomposition helps us to reduce things to proofs that are still pretty simple. I mean, the proofs in CertikOS, there aren't many code proofs that are actually much more complicated than that because we managed to decompose everything in very simple components. So, yeah.
All right, so I'm supposed to have 30 minutes to talk about this second half of the lecture today. but I don't. So, so I will just preview what I want to talk about. So on the third lecture, I'm going to show that how to prove information flow security of a 3,000 line of a CertikOS kernel, but mostly staying at a high level. So we have an artifact so we haven't made any official public release of any of our CertikOS OS yet, but we have an artifact available through this PLDI 16 paper, which actually contains the full source code. So you can view this as a private public release if you know where it is. But we didn't intend for people to work on this version because this is a version that kind of obsolete. That is the one that based on our previous infrastructure. But you can actually download the full tar file. There's even a VM VirtualBox image. And you can, this only compiles under Cork 8.4 with the early version of CompCert. And one of our work right now was to port this work and our concurrent CertikOS work into the new framework based on the layer library that Jeremy has implemented recently in Cork 8.6 and based on CompCert version 3.0.1. So, but if you want to see what the current version of want to see a particular version of the CertikOS proofs, you can browse this thing in the in this artifact website where it shows how do we divide OS into basically about 37 to 40 layers, and how do we actually combine these things together, okay? So what I was originally planning to do today is to go through some of these layers with you. I think I can probably still briefly mention how this work was done. Let me see. So the idea is that with these layers, I should be able to explain the internal of an operating system kernel that can bootstrap Linux in 30 minutes of lecture that you can actually see that, oh, this is actually how a layer OS works, and each layer looks totally almost trivial because it's look like the layer that Jeremy has showed, but when you compose them together, you actually build something pretty powerful. So I wouldn't be able to do it today, but I will do it on Thursday's lecture, and then followed by description, how do we prove information flow security on top of the DeepSpec. But for the rest of the last 5 minutes, I just want to come back to the lecture we were talking about in yesterday's lecture, that just to give you what we have done in the CertikOS toolchain. So this is so we essentially define these so-called layer specifications, and we modify the CompCert compiler from CLite to ASM, and we change the C language so that now each of these C language can be parameterized over these layer interface, which could be any of these layer interface. So this is really just almost identical to the C language, except now you have access to all the primitives available in that layer L. So this is what we mean by CLite XL language. So at every abstraction layer, you get somewhat new language, but it's really just C. And on this layer L, you can write those C programs where you can have M and N components, and you can do composition of it. And then we extended this C-Lite CompCert compiler, which we converted into so-called CompCert XL compiler, which means I can compile those C-Lite X into some version of assembly language. So in order to support OS kernel functionality, we extended the assembly language with more low-level kernel features, virtual memories, and that language is called LLSM. And LLSM is also parameterized over this layer interface. So this layer interface, you can imagine that actually defines what abstraction level you are at. So if my OS has 37 layers, I could have a 37 layer interface. But Jeremy actually talked about even between these two layers, we have these low-level spec and high-level spec. And so we actually have many more layers than just what you see in the when we see the spec of the kernel itself. So then this CompCert X, of course, at the assembly layer, you can handwrite. You can also have these handwritten assembly code verified in this LSM AL language. And that, for example, you can produce routines like a context switch. And then this CompCert XL compiler will compile C-Lite XL to LSML. And then we can take those layers that you verified at C, and the CompCert X will generate the layer that's verified at assembly layer. And then this layer library will help you basically put all these things together. So that's the kind of a big picture that we have. And so this just shows you that the things we do. We can have vertical composition. We can actually have a horizontal composition. But when you do the horizontal composition, you have to make sure that the abstract function or abstract relation is identical when you compose two modules at the same abstraction level, because otherwise you would create conflicts. Because if you one abstraction view the state in a certain way, another one did it in another way, the invariants may be in conflict. So this won't work if you have different abstract functions. So you have to make sure they use the same abstract function or abstract relation R. And then you can do the horizontal compositions. And then if you have a C certified C layer that, let's say we have already built those, we could actually compose with the CompCert theorem. And this CompCert X theorem will say that there's a forward simulation through some kind of a memory injection relation m-inch that from the you can prove the simulation relation or refinement relation from the C-Lite code to the corresponding assembly code. This CompCert XL to MC, and from that you can compose these and show that this assembly layer is also when you compose these two simulation relations, is also a certified layer. And by doing this, you essentially get back a certified assembly layer. So of course, this mapping is not as simple as this in practice, because there's a C calling conventions where you have to map the C calling convention to the assembly level, which passing arguments following fixed convention. So what originally I want to cover was to show how do we actually apply this to the kernel, but we are out of time, so I will do it on Thursday. Okay, but the homework for today is to solve some of the exercises left in the stack.v. And if, of course, you have questions for counter.v, many of my students and will be here answer this afternoon. Yes?
So if I understand right, you're basically extending the machine abstraction of assembly languages to mean kind of OS function, scheduling, giving you and stuff like this?
Yes.
Have you looked at LLVM OS, which is basically an extension of LLVM that extracts similar things? I was wondering if you've seen it or its relationship to
Is it a LLVM virtual machine, or
Yeah,
is the one at UIUC or?
yeah. So there was a paper at SOSP called SVA.
Yeah, I think I know that work.
SVA
Right.
extended LLVM with the operating system abstraction, similar to this. I was really interested.
Well, what we are doing is, I think they probably don't address issues like paging, virtual memory, and adding concurrency primitives like C switch, because many of these abstraction layers we create really change the way you view memory. You view introduce multiple threads, and so I think they are mostly focusing on probably user level code rather than kernel code.
Actually, it inserts the same as a thin hypervisor at the same abstraction layer. So
Okay.
MMU, virtualized schedule switching. Basically, it removes assembly from the kernel,
Okay.
and then you splice this thing in. But it doesn't do any verification.
Okay.
It's not layered. It's just a single, hey, let's take all the assembly, let's throw it into this single kind of in-kernel component,
Okay.
and then you abstract this API to the rest of the kernel.
All right.
So it's just a single layer.
Okay. Good. All right. I think it's time for lunch. Good work. I was hoping you leave me a little bit more time.
Yeah, I noticed the time flying by, but since you told me,
No, it's fine. You can take as much time. That's okay. I don't know how to turn this thing off. Maybe it's turn off automatically.
oh, you need to stay on the off button for a while.
That's it. Yes.
Imagine what you're saying is, well, we remove all the assembly and convert them into functions in this trusted component, and then there's this layer of software installation and other techniques that isolate them. And then my way is basically, let's remove the compiler. Nick. Yeah, sorry.
Where are you?
I was at Koenig. I graduated something like Berkeley. Yeah, sorry about that. I sent you an email with some of the details.
That'd be great. I would love to look at it. Yeah, so
There's a lot of really cool stuff there. I'm excited to think about all the ways that you can integrate both.
I'm actually very interested to see the possibility of getting some kind of LLVM bytecode as a more, platform independent thing, because there's an interest about doing something for blockchain world, like these EVM and so on. Not have as many support. So there was the idea that maybe, combining what we do with more LLVM bytecode, and then with what Steve has been doing at the we can do something.
So Steve and I actually just wrote
John, we have our lunch meeting.
Oh, okay. I'll be coming.
All right.
Yeah. In 2 minutes, okay? Yeah.
So actually, Steve and I wrote about an IR that basically automates the mechanism of LVM stuff, and then, but the OS level representations are also something that I'm looking at as well. And I'm actually looking at some other space. I'm looking at modeling kind of privileges. And it's a higher abstraction layer than what we're talking about, but in some sense the API, the encapsulation, so yeah, very cool. And we actually have released the SVA stuff, the IR OS.
Okay.
We have that.
So send me email. I will look more at it. Yeah. Yeah.
object.